Good evening, sir.
Hello guys, good evening all.
Good evening, sir.
Okay, so yeah, it's time. So we are going to start a new chapter today, that is Carbene. Aromatic chemistry, few reactions of benzene, that is aromatic compound, we'll see in the last. We'll start with first carbene. Carbene is like another intermediate, carbocation, carbanion, right? It is also an intermediate which forms during the process of a reaction. So first of all, we'll see today what is this intermediate, that is carbene, how it forms, what condition we have for the formation of carbenes, and what reactions we have which involves this particular intermediate, that is carbene formation. Okay, like last class, last chapter, if you see, we haven't discussed this one, Riemer Tiemann reaction, and I told you it involves carbene intermediate. That reaction and other reactions also we'll see in this particular chapter, correct? So in this chapter, we are going to have few reactions of alkene, few reactions of again carbonyl compound, aldehyde, and ketone. So parallelly, you see from the last two chapter, if you see, we are doing different reactions of carbonyl compound. So when we start after this, when we see aldehyde and ketone, aldehyde, ketone, carboxylic acid, again there will be only few reactions left. Okay, so that's how the thing is. I'll let you know what all reactions you have to study from different chapters. I'll just tell you when it comes. So we'll start with the chapter. So write down first of all carbenes. Heading, write down. 1 second, just 1 second. Okay. So what is a carbene? Carbene is, write down, carbene is an electron deficient neutral carbon containing intermediate. Carbon containing intermediate. Again, one more thing, guys, I'd like to add you here. I'd like to tell you here that this particular topic, carbene and its intermediates, you won't get any. No, just a second. I'm getting a call. Just a second. Right. So you won't get any separate assignment on this because this is not a chapter. Okay, it is a intermediate, and there are reactions which based on this intermediate. So those reactions are there in different chapters. Okay, so you will get that in respective chapters question based on this. Okay, so that is one thing that you must keep in mind. Right. So what is a carbene? Carbene is an electron deficient neutral carbon containing intermediate. The other electron deficient carbon containing intermediate are, any example? Any example? Electron deficient carbon containing intermediate?
Free radical.
Free radical. What about carbocation? That
So
is also an electron deficient carbon containing.
So that's not neutral, right? So
non-classical carbocation.
Non-classical carbocation, yes, you can say that. Non-classical carbocation also, and carbocation simply also. All these are electron deficient carbon containing intermediate. Okay, so like carbocation, carbanion, free radical, carbene is also an intermediate. Okay, what type of intermediate? Electron deficient intermediate. Okay, so what is the, like, there are two types of carbene we have basically, right? Carbene we have of two types. The first one is singlet carbene. The first one is singlet carbene. And the second one, don't write it, we'll see that later. And the second one is triplet carbene. Singlet and triplet. Okay, so what is singlet carbene first of all?
So what's the other type?
Triplet, T-R-I-P-L-E-T, triplet. We'll discuss after singlet, we'll see that. Okay, don't write it. So singlet carbene is the carbon atom which has two atom attached to it, atom or group, anything, XY, one lone pair and one vacant orbital. This is the singlet carbene. 2 sigma bond, 1 lone pair, 1 vacant orbital. Okay. So, yeah.
So carbenes are always intermediates.
Sorry.
Like, are carbenes always intermediates, or can they exist on them?
Carbene intermediate. What did you say? I didn't get you. Your voice is breaking.
So,
You
like,
said carbene.
is it only intermediate, or can it be like can it exist freely on its own?
No. Like it is similar to like as far as the stability is concerned, it is existence is concerned. It is similar to the other intermediates. Like it won't form as a final product in the reaction. This can be a part of a reaction. Means intermediate. You have substrate, right? Substrate reacts and it forms intermediate. If the condition is there that intermediate converts into product, or it converts back into the reactant, the substrate that you have. Means it won't be the final product of any reaction.
Okay.
Okay. So the properties of singlet carbene, you see, if you know this particular structure, you can write down all the properties together, because sometimes in the exam they'll ask which is the correct statement regarding carbene intermediate or singlet carbene intermediate, right? So for that, you just need to know the structure. Carbon has 2 bond, 1 lone pair, 1 vacant orbital. So the first property is it has 2 sigma bond, as you can see, and 1 lone pair. The second one is it has 1 vacant orbital. The third one, it is neutral. There is no charge in this. It is neutral. Number of electrons in this bonding state for carbon, it has 6 electrons. 6 electrons in the outer shell. Okay. Another thing, since it has 6 electron, 1 vacant orbital, so it has incomplete octet. Right? sp2 hybridized, bent shape. Electrons are paired, so it is diamagnetic. And electron deficient, electrophile, or behaves as Lewis acid also. Electron pair acceptor. Okay, this is the property. If you find out spin multiplicity here, spin multiplicity, the formula is 2 summation of S plus 1. So we have 2 electron, one is plus half, other one is minus half configuration. 2 into plus half into 1 plus minus half into 1 plus 1. So this is 1, you are getting value. Since it is 1, hence it is singlet carbene.
So what is spin multiplicity?
Spin multiplicity is because of the orientation of electrons in the orbital. We calculate with this sigma spin quantum number. One electron is clockwise, other electron is anti-clockwise. Okay, so its orientation about itself, if you see the axis, one is plus half, other one is minus half. So for both the electrons, if you count the spin multiplicity for the outermost electron, it is plus half into 1 minus half into 1. This formula just we substitute here and we'll get the answer.
Okay.
It is because of the orientation of electron. Many things into that. It is quantum mechanics actually. The orientation of electron along the magnetic field, if it is, then it is plus half the value is. If it is opposite to the magnetic field, it is minus half, and that is the significance of a spin quantum number. Okay, but that is not, I'm not going into detail of all those. Just the value spin multiplicity is coming out to be 1. Hence, it is singlet Carbyl. Did you copy all these?
Yes.
Now, one very strange property we have here that probably you did not notice. Otherwise, you would have asked that question to me. See, the point is carbon has, how many electrons this carbon has here? Only for carbon I'm talking about, not for this X and Y. Carbon has 4 electrons, right?
Yes, sir.
1, 2, 3, 4. So, and this orbital is vacant, which is not possible according to Hund's rule, right? Yes. According to Hund's rule, all the electrons must have, all the orbitals must have 1 electron each before pairing, right? So this electron, which is there in the orbital, it should be the normal rule that we have according to Hund's rule. It should be here in this orbital, correct? So basically, this particular carbene, that is singlet carbene, we can say it does not follow Hund's rule. This is very important. This is very important, right? Does not follow Hund's rule. It forms during the process of a reaction, and there are some conditions which stabilizes this carbene, singlet carbene. Under those conditions only, the carbene forms. Otherwise, this singlet convert into triplet. Okay, so in any reaction, first of all, we'll get singlet carbene only. First of all, singlet carbene only forms in the reaction. If those conditions are there, those conditions to stabilize this carbene, if those conditions are there, fine. Otherwise, it converts into triplet. That is how the triplet carbene forms. What are those conditions? We'll discuss that later. First, let me just finish this. The 2 types of carbene we have. So singlet carbene, spin multiplicity is 1, and all these property we have. This one is the most important one. It does not follow Hund's rule. Okay. Now the second type you see here, the second one is triplet. Triplet carbene, you see, carbon again has 2 bonds and it has 2 unpaired electrons. Or we can also represent this as X, C, Y, and 2 unpaired electrons present like this. You can simply understand this from here. If this 1 electron goes into this orbital, then this becomes triplet carbene. That is the only difference. Okay. So first thing, in triplet carbene, none of the orbital is vacant, right? Vacant orbital is not there. Pranav will discuss that. Why it does not follow Hund's rule, we'll discuss. Because in the reaction, yes, Advik, that's right. In a reaction, like I said, first this singlet carbene forms. If there are the condition of that, to stabilize the singlet carbene, then it will be remain as it is. Otherwise, it will convert into the more stable form, which is this triplet carbene. So triplet carbene follows Hund's rule because all the orbitals are occupied here. Okay.
So how can it form that first one? That doesn't even follow Pauli's exclusion principle.
Pauli exclusion principle, why? Why it does not follow Pauli? What is Pauli exclusion principle?
So like those 2 electrons which you drew on top of carbon, are both of them in the same orbital? Because
no, it's not. See, I cannot show you all. No. You can come.
Okay.
If it is in the same orbital, then one is clockwise, other one should be anti-clockwise.
Yeah.
So these 2 are in different orbitals. That's why I have given only up-headed arrow. Yes, it's just a notation. No. See, you can, if you see, actual thing is what you draw this p orbital like this. Both way you can draw, both way you can think of. You see, two p orbitals has one electron each. This way also you can write. This way also you can write. What is the problem in this? You can write on this way also. So in the book, if you see, if it is given, but however in all the books, these things are not given. Okay. So they write like this also and like this also. Did you get it? See, you cannot assume that both electrons are present in the same orbital only because it is written just side by side like this. If they are in the same orbital, one is clockwise and then other one should be anti-clockwise. If both has the same orientation, it means both are present in different orbitals. Clear now?
Yes, sir.
Fine. So if you talk about the first thing, we can finish it off here only. If you talk about the stability of singlet and triplet. So obviously triplet one has symmetrical arrangement of electrons. So triplet carbene is more stable than the singlet one. Okay, that is also one thing you must take care of. Write down triplet is more stable than singlet. Okay, property you see, it has two sigma bond, but there is no lone pair. It has no vacant orbital. No vacant orbital. Two unpaired electron. Two unpaired electron. And once it has unpaired electron, it means it is what?
Aromatic.
Paramagnetic. So all these property you see, I'm just writing down with this structure. So I request all of you to just keep this structure in mind, and then whatever the question you have in the paper, accordingly you can answer that. Okay. It is sp hybridized, linear also. It is linear. Spin multiplicity, if you count, it is 3. With the same formula you count, it is 3. Both are clockwise, and hence it is triplet. The next one is it has 6 electron in the outermost shell. 6 electron in the outer shell. Since we have 2 unpaired electron, 2 radical, so it is biradical. Follows Hund's rule. This property is very important. Follows Hund's rule. And that is it. Okay, these are the properties we have of triplet.
So what's biradical?
Biradical means we have 2 radical, 2 unpaired electron. No, what is 3 radical? 3 radical means 1 unpaired electron, right?
Yes, sir.
If you have 2 unpaired electron, this is biradical. Stability you have written. Triplet is more stable than singlet. Done. Okay, so these are the 2 types of carbene we have. Now, under what condition this carbene forms?
So commonly we'll find triplet carbene only, right, in reactions.
Sorry?
So in like reactions, more commonly we find triplet carbene only, right? Because it's more stable.
No, it depends. It depends. It depends. I know you have some doubt. After half an hour, you won't have these doubts. Okay, just give me some time. Okay, let me just go through it. Okay. So whether in the reaction carbenes or like singlet or triplet forms, that depends upon the reaction conditions, solvent plus what a substrate we are taking, what reactant we have in the reaction. All those factors we have. Okay. Few more minutes, like 15-20 minutes, you will understand all this. Okay. So the first condition under which carbene forms is this. We have a reaction, for example, we can take CHCl3, chloroform, and reaction of chloroform in basic medium. KOH you can take NaOH. Okay, you must have seen few reactions in which these reagents are present. Okay, this converts into CCl2 plus KCl plus H2. CCl2 carbon has one lone pair and one vacant orbital. So this is singlet carbene. This is singlet carbene. Correct. How this reaction proceeds, you see. If you look at this molecule, right? So this hydrogen, because of 3 minus I effect of chlorine, 3 minus I group we have here, carbon with 3 chlorine. And because of this chlorine, this hydrogen becomes acidic. And that's why in basic medium, if you take any base here, then we'll have acid-base reaction. That is OH minus takes this H, forms H2O, and it forms here carbon with 3 chlorine. Plus H2O. Okay. After this, this chlorine, one of the chlorine goes out as a leaving group, and this converts into carbon with 2 chlorine, 2 sigma bond, 1 lone pair already there. And since chlorine takes up the 2 electron, goes out, this has one vacant orbital, and it forms Cl minus here. This Cl minus takes this K plus, so form KCl and H2O we already have. Copy it on this.
Sir, isn't the second one negatively charged CCl3?
Copied.
So 1 minute.
Sir, isn't the second one negatively charged CCl3?
Negative charge?
So yes,
Here,
because
here,
OH
here, no.
minus was negative. Yes, sir.
Here. Yeah, here we have the
Yes.
negative charge. And then when this Cl minus goes out, here we don't have any charge. So this one is chloroform.
So So you can carry on.
Okay. Now you see this dichlorocarbene. The name of this carbene is, it is dichlorocarbene. This dichlorocarbene is actually stable here. If it is not stable, then it converts into triplet. One electron, it jumps into the vacant orbital and will get triplet carbene finally. Okay, and the reaction will go according to triplet carbene. Okay, but how this this carbene is stable? It is stable because of the back bonding of this chlorine atom. This back bonding tendency we have, so it occupies the vacant orbital and the octet of carbon is complete, right? So this is stable because of, write down, it is stable because of back bonding. So this is one of the condition of the stability of this carbene because of back bonding. Okay, purpose is the octet of carbon should get complete here, right? And that will get complete when it donates electron pair to this carbon atom, which is happening here due to back bonding. If you have any polar solvent also, like suppose H2O, which a polar solvent which has at least one lone pair present on it, so those polar solvents also stabilizes this carbene by the donation of the electron pair which is present on it. So when you have these two conditions, right, whether it is, the first one is back bonding. Suppose we have one carbene like this, hydrogen. In this, we do not have back bonding, right? This singlet carbene is not stable in this case, if the solvent is not polar, right? But if you have CCl2, then singlet carbene is stable here because of back bonding. So two conditions are there for the stability of back bonding. One is back bonding and other one is presence of any polar solvent which has at least one lone pair on it. Okay, I'll just dictate you just a second. No. See, all of you just try to understand this. We are not talking about reactions here. This is not a complete reaction. They won't give you this reaction and find out what is the product, because this is an intermediate. An intermediate cannot be the product of any reaction, Dhruv. Okay, so when you get the question in the test or exam, this reaction is a part of the main reaction. You will have some other reactions, but this is one of the steps in between you have. Did you get it, all of you?
Yes.
Right. So this you must take care of. These are not complete reactions. When we finish, there are 4 conditions of the formation of carbene. When we finish that, we'll see what all reactions we have which involves carbene. Right. So all these 4 conditions are not, the complete reaction. So write down into this. Singlet carbene gains stability. Singlet carbene gains stability due to back bonding, like in this case, or in polar solvent, which contains at least one lone pair on it. So if it is CS2, you see here, polar solvent contains at least one lone pair on it. If it is CS2 and suppose we have solvent is water here, then this singlet carbene is stable because water can donate its lone pair onto this singlet carbene and the octet of carbon is completed. So this is the 2 cases where the singlet carbene is stable and it forms. If these 2 cases are not present, it converts into triplet, which has more symmetrical arrangement and more stable. Okay, so in this reaction, we can take base here because this is the acidic hydrogen, active hydrogen, and we can take any base for this reaction to proceed. Okay, The base could be, we can take OH minus for this purpose. We can take NH2 minus also. We can take RO minus, PHO minus. All these bases we can take for this reaction. Understood? See, Varun, there's one, all these, when I talk about stable carbene and unstable carbene or less stable carbene, this is all relative, right? It does not mean that the intermediate carbene is stable or unstable. Means singlet is slightly lesser stable than triplet. That is what it means. But it is not that much stable. The triplet one is not that much stable that it would affect the rate of the reaction. It is, both are intermediate only. So they are highly unstable. But if you compare singlet and triplet, triplet is more stable than singlet. So it is relative between the two. Okay. Fine. So these are the bases we can take for this reaction. Okay. Could you tell me what is the singlet carbene you get in this particular reaction? If possible, then suppose we have CHCl2Br and this reacts with KOH, NaOH, anything you can take. What is the carbene forms here? No, that's not right, Pradyut. Yes, now it's fine. Now it's correct. Got it, Pradyut. Okay, so I think all of you have done this. First step is this OH minus. No, that's not correct, Param. This OH minus takes what? Takes H plus and forms H2O. That is what the purpose of base. And then we'll get carbon with 2 chlorine and 1 bromine with lone pair on it. Then one of the halogen atom comes out, right, as a leaving group. So which bond is easier to break? Carbon chlorine bond or carbon bromine bond?
Carbon bromine.
Carbon bromine. Why? Because the carbon,
So
it has more, the bond length is more for carbon and bromine, right? So bromine comes out easily, right? And it forms KBr with CCl2, 1 lone pair and 1 vacant orbital. So carbene is dichlorocarbene here also. Will this convert into triplet?
No, sir.
No,
Back
because
bonding,
again we have back bonding we have, so triplet won't form into this. Singlet is the final one here. So like this, they can give you CHClBri, another one. So always remember that the 2 bond, which is the most strongest bond out of the 4, obviously hydrogen will definitely go with base. So other 3 bonds that you have, among those 3 bonds, the 2 stronger bond will be here with the carbon atom. Like suppose if I ask you, we have CHClBri with base OH minus. Tell me the carbene directly in one step. What we get?
CClBr.
CClBr, yes. ClBr, lone pair, vacant orbital plus Ki plus H2. Okay, simple logic we can apply. Fine. This is the one case under which the carbene formation takes place. Always remember, these are not complete reactions. I'm repeating this thing again and again. These are not complete reactions. Okay. Now the other condition under which the carbene intermediate forms, the second one is tetrachloromethane, chlorine, 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 and this chlorine. Right. From this, we need to form carbene intermediate. Could you tell me what is the possible carbene intermediate we get from this? What is the possible carbene intermediate? Means what are the two atoms which attach with the carbon atom in carbene?
Cl.
So both
Chlorine,
chlorines.
Two chlorine atoms.
because yes, because there is no other way. Other options are not there. Only chlorine is there, right? So if you compare this with the previous one, instead of one hydrogen, we have one chlorine. That is the only difference we have. Yes.
Yes.
So like we removed in the first case, like we removed this hydrogen with the help of a base. Similarly, if you are able to remove this chlorine atom with the help of some reagent, then we'll have the similar reaction. Yes or no?
Yes.
Correct. So the purpose is here is
So that chlorine comes out as a electrophile.
No, just a second. The purpose here is that we use some reagent here in order to remove one of the halogen atom. Clear? So what we'll use here, we'll use a stronger base with the help of a metal, that is R minus Li plus. This R minus Li plus, it takes this Cl, forms RCl plus CCl3, one lone pair, right? And from this CCl3, again the same step we have here, one Cl minus comes out, forms CCl2, one lone pair, one vacant orbital, and this Cl minus is taken up by Li plus, forms LiCl. The reagent here is R minus Li plus.
So again in the second step, will we have a negative charge on the carbon?
Yes, we'll have. I forgot to put this. Obviously, we'll have. Because what happens, it goes like this. R minus, it attacks onto this chlorine, one of the chlorine. Obviously, if you have 4 halogen atom, then the bond which is the weakest bond, on which this, on that bond only, on that atom only, this R minus attack, and this pair of electron it shift onto this carbon atom. So obviously here we have the negative charge. Correct? So reagent is R minus Li plus we are using. CCl4 is the substrate here. It is not a solvent, first of all, Ruchir. The second point is the carbene that forms, this carbene is stable because of the back bonding. Correct? So it is not a solvent. Carbon tetrachloride is a substrate here. Plus back bonding is there. Okay. One example in this, you see. Suppose I am taking CH3, CBr, ClCl. The reagent is CH3 minus Li plus. Tell me the carbene that forms here. That's not correct, Ruchir. Yeah, Rahul, that's right. Correct, Varun. No, Mehul, that's not right. Correct. Here, that's right. Where is Akshita? Akshita, Akansha, are you there? Anush, Chaitanya,
Yes, sir.
Yes, sir.
are you getting it, all of you? Akshit, what is the answer, Akshit? Tell me.
So I'm still doing.
Yeah, that's correct, bro. See, first of all, what happens, like here you see the reaction here initiates with the attack of this R minus, and this R minus will take the weakest bond, the atom which is attached with the carbon, and the bond should be the weakest there. So this R minus takes this Br first of all, because this bond is the weakest one, right? So it forms CS3Br, and then carbon-carbon bond won't break because chlorine obviously is a good leaving group. It goes out in the next step. So CS3C, we have two chlorine atom here and a lone pair negative charge, and from this Cl minus goes out as a leaving group taken up by Li plus. So it is LiCl, CS3, CCl, lone pair vacuum product. This is the carbon intermediate forms. Okay. All of you write down 2-3 points here. Note. Write down in any reaction. In any reaction, singlet carbene forms first. Singlet carbene forms first. Singlet carbene forms first. And if the medium of the reaction, and if the medium is non-polar, if the medium is non-polar or gaseous phase reaction, if the medium is non-polar or gaseous phase reaction, or in absence of back bonding, medium is non-polar or gaseous phase reaction, or in absence of back bonding, the singlet carbene converts into triplet. The singlet carbene converts into triplet. Next point. These reactions are not complete reactions. These reactions are not complete reaction. And it can be a part of any other reaction. and it can be a
Sir,
part of any other. Yeah.
sir, over like here, I still don't get why CH3 won't go and attack the other CH3. Because over here, the like bromine will have to become Br plus. So isn't it much more stable for CH3 to become CH3 plus?
I don't get you. You're talking about that
So
which
this
CS3, the reagent one or this one? Which one you're talking about?
the one which is getting attacked, like the carbon, bromine, chlorine, CH3. Why
Okay, this
doesn't
one.
the yes, sir? Why doesn't the reagent go and take that?
This one. See why this will attack over here. That is because the bond is polar here, right? Carbon, bromine, there is electronegativity difference. Here we do not have any electronegativity difference between carbon and carbon. So this is the partial positive charge on this, this and this. This will attract the R minus ion towards its side. That's why this won't take this carbon from here. And anyways, carbon-carbon bond is covalent bond. It is difficult to break this bond in
Okay.
comparison to the other bond, that is carbon-bromine bond.
Okay.
Okay. So did you write these reactions are not complete and it can be a part of any other reaction? These are the two conditions under which the carbene intermediate forms. You should just keep that in mind, that what reagent we are using in this reaction, right? Because in the reaction, one of the steps would be like this, and you have to identify that the reaction involves carbene intermediate, and then you can think of the product accordingly. The third reaction is under which the carbene intermediate forms. From there only I started, Advik. Just one line I said that in the reaction, carbene intermediate always forms first, and then if the medium is nonpolar. In any reaction, carbene intermediate always forms first, and then if the medium is nonpolar or gaseous phase reactions, or in absence of back bonding. Done, Advik? Okay. So the third reaction is with diazomethane. Diazomethane, now we'll have the reaction of diazomethane. It is there in nitrogen containing compound also. And these reactions are important also, and very simple one. Everywhere we have similar kind of reaction. Diazomethane is this. This is diazomethane, CH2N2. Diazomethane, if you heat or high temperature also, if it is written fine, because both are the same thing, or in presence of light, HB, any one of the three conditions here. This converts into carbene and nitrogen gas evolve. Okay, but since this carbene is singlet and there is no stabilizing factor here, further this converts into triplet carbene, which is this. This one is triplet. So with diazomethane, we are getting triplet carbon. How it happens, you see, very simple mechanism. One of the pi electron, pi lone pair converts into pi, and this pi converts into lone pair on this side. So it is just the resonating structure, and we get this CH2 lone pair negative charge, single bond N, triple bond N, one lone pair on it, positive charge on this nitrogen, and then since we are heating it, this N2 eliminates, and two electron pair is taken. one electron pair is taken up by this nitrogen, electron deficient nitrogen. The orbital of carbon here, it is vacant. Oh, I'm sorry. And then it converts into triplet. This is how the reaction forms. Fourth and the last condition for the formation of carbene is with ketenes. Ketenes I'm writing down here. I won't write down the mechanism. It is exactly same like we have in diazomethane. Ketene is this CH2 double bond C double bond O. Same thing we are doing either heat or high temperature or in presence of light. This converts into HC H triplet carbene plus carbon monoxide gas evolves into this. You can compare this, it is similar to the previous one. Instead of this nitrogen, we have this oxygen, and both atom you see has two lone pair. This one has no lone pair here. When it comes over here, this goes here, and then next step will go like this. Done?
Yes, sir.
Okay. So these are the four conditions we have under which carbene intermediate forms. In the question, you can get any one. Okay. All these are not complete reactions. Okay. And based on the reagent, you can identify the reaction. Okay. And then we can see what products possible in the reaction. Correct? Okay. Now, we'll see the next thing, that under what is the reaction, what are the reactions we have which involves carbene intermediate. Okay, so write down the heading, reactions of carbene. Reaction of carbene. There are total 8 reactions we have to study, that is there in our syllabus. The first one is addition on alkene. Addition on alkene. The second one is carbyl amine reaction. Third one is Riemer Tiemann reaction. Riemer Tiemann reaction. The fourth one is Arndt Eistert reaction. Reaction on carbonyl compound. On carbonyl compound. Insertion on alkanes. Insertion on alkanes. acid-base reaction. Simon-Smith reaction. These are the 8 reactions we have which involves carbene formation. One by one, we'll discuss all. All these reactions are very, very important, okay, except the last ka 2, 3. Right? Simon-Smith is not much important. It is very much similar to the first type, addition on alkene, okay? But the first 5 reactions are very important.
So the third one, what's it called?
Riemer-Tiemann reaction.
Okay.
Riemer-Tiemann. Copied, all of you? Done? Can I move on? Mehul, Rasdeep, are you done?
Yes, sir.
Yes, sir.
Okay. So first reaction, write down addition on alkene. Write down this reaction involves both mechanism, singlet and triplet carbene mechanism. This reaction involves both mechanism, singlet and triplet. Okay, so look at this reaction. One more thing we'll see first. It has 2 different mechanisms, singlet mechanism and triplet mechanism. The basic difference in these 2 mechanisms is the singlet mechanism, the reaction is stereospecific. And this one is non-stereospecific. The term also you must remember, non-stereospecific. Stereospecific means what? Stereospecific means if you have taken cis molecule, means cis alkene gives you cis product only. It won't give you trans. Trans alkene gives you trans product only. Okay, non-stereospecific means what? If you're taking cis alkene, then you do not have any control here. You can get trans, you can get cis both. You get both product into this one. That is what it means, non-stereospecific.
So
Okay.
even for trans also, right? Like trans
Yes,
alkene.
yes. Trans also gives you cis and trans as well. Okay. Now you see, Look at this reaction, all of you. Suppose we have a cis alkene which is CH3, C double bond C, CH3 H, and this is allowed to react with CHCl3 with KOH. Okay, what is the first step here? Could you tell me?
Singlet carbene formation.
First step is the formation of Carbyl. So this CHCl3 and KOH, you see the first condition I have given you. It is the same thing, right? So this CHCl3 and KOH reacts with each other and it forms first carbene. And what kind of carbene we get here? We get here singlet carbene. So I'm not going to write down this reaction again because we have already done it. Okay. So I'll just write down here the carbene that we get. The carbene that we get is what? We get CCl2 and a vacant orbital. This carbene, you see, this carbene interacts with this alkene. So how it happens, you see, the carbene C has lone pair and one vacant orbital. This interacts with the alkene. So it gives its lone pair to this carbon. This sigma pi bond comes over here. And this lone pair, it again donates to this vacant orbital of this carbene. So what happens here? We get carbon-carbon bond as it is. And with both carbon atom, this carbene attached this way. And if it is cis, so we'll get here CH3, CH3, H and H will be as it is. So this is the product we get in this reaction. It is singlet mechanism. Okay, singlet mechanism. So we'll get only cis here. Write down here on the top, singlet mechanism, or here singlet.
So what's this product called?
It's a cyclic product. No, so you can name this IUPAC name. You can do this. It's not like a common name. We do not have for this.
So is this the final product?
Yes.
Oh.
So you wrote CH by mistake, so right side.
I wouldn't see it. It's H only, not CH. So this is the product we have. Okay, one side addition of this. One more thing you see, in this carbene, we also say we have two different ends. Like you see, this the lone pair that you have, this we call it as nucleophilic end. Nucleophilic end. And this one we call it as electrophilic end. Electrophilic end. So nucleophilic end attacks here, electrophilic end receives the electron. Got it? Now the triplet mechanism you see. The triplet mechanism is actually factual a bit. Okay, this one term you should keep in mind, but it is factual. You have to memorize the reaction. You see what happens in this. Like we say, it is a non-stereospecific reaction. C double bond C, CH3, H, CH3, H, and this is allowed to react with CH2N2 H nu. CH2N2 H nu, it gives what? It gives triplet carbene. There is no stabilizing factor. We get triplet carbene here. And this triplet carbene, first of all, I'll write down the product. The product that we get here is carbon-carbon. We have 2 hydrogen, CH3, CH3, H, and H. And the other one is carbon-carbon, CH3H, H, CH3H, and this is CH2. This is the product we get. Cis and trans, both product we get here. Okay. Now you see this molecule, how the reaction proceeds. Carbon-carbon double bond, CH3H, CH3H, and this carbon, this reagent gives you triplet carbene, which is this. Okay, so see this pi bond I'm just removing from here. And we can say this double bond that forms, one electron is clockwise and other one is anti-clockwise. That we can say. Then only the bond forms. When this carbene forms, the triplet one, and it starts interacting with this pi electron of this molecule, then the electron of carbene and the electron of this carbon, which has the opposite spin, clockwise, anti-clockwise, can easily interact and forms a bond over here. Right. So carbon-carbon single bond, CH3H carbon, and it forms a bond here, H, H, and a lone pair here. Sorry, not lone pair, a single electron we have here. And this has one hydrogen and this has one CH3. Now, since both the electron has same orientation, so they cannot form a bond here. Obviously, the rotation has to change, right? Orientation has to change. One electron must go anti-clockwise, the orientation has been should be in anti-clockwise, then only the bond formation possible, right? So in this process, what happens when it starts interacting, this pi bond actually it dissociates and it converts into a sigma. So because of sigma bond here, single bond, we have bond rotation possible here. We have bond rotation possible. Earlier, the bond rotation was hindered because of the pi bond. Rotation across pi bond is hindered, right? But here the rotation is not hindered now. So sometimes what happens to make this bond, to have the difference in orientation here, sometimes this bond itself rotates and sometimes this spin, the electron itself rotates. So if bond rotates, then this CH3 will come over here, this H will go up, right? And we'll get a trans product. But if this spin rotates and this carbon-carbon make a bond, then it is cis product. So that is why we have two products we get here, and the reaction is said to be non-stereo specific. We also say a term here that the time required for a spin inversion is generally more than the bond rotation, right? Spin inversion means conversion of clockwise into anti-clockwise. Spin inversion, right, is more than that. But sometimes we have, same product without bond rotation, and sometimes we have bond rotation and we'll get the other product, right? That's why we have the possibility to get both the products in the reaction, and the reaction is said to be non-stereo specific. Last thing, this reaction, this mechanism you don't have to memorize, but property you must keep in mind. Yeah, tell me.
How does spin inversion exactly work?
Spin inversion?
Yeah. So,
What?
like, how is it like possible?
The electrons, the rotation of electron, you have no control. Like suppose if the electron is going into one particular orbital, correct? It has one particular spin, maybe clockwise, maybe anti-clockwise. We do not know about it, right? And when the second electron goes into the same orbital, then the second electron definitely have the opposite spin to minimize the repulsion of the electron, correct? It happens
Yes.
on its own. Similarly, when this carbon-carbon bond forms, and this carbon starts interacting with this carbon, and this interaction is possible when these two comes closer, and when it comes closer, so other electron, to minimize repulsion, it rotates in opposite direction, and that is the spin inversion.
Okay.
So,
Correct? So like I said, we do not have any control on this. It happens on its own, and this
sir,
has been observed. Yeah.
so you told time for spin inversion is more than bond rotation. So can we say trans is more easily, like more
Yes, we
quantity?
can say that. We can say that bond inversion is more easier. Means bond inversion is easier in comparison to the spin inversion. So whenever the bond inversion takes place, you'll get a trans product. So you can say trans will be little more in the mixture, but we'll get both product in the reaction.
Okay, sir.
Understood? So the triplet mechanism is non-stereo specific. Singlet mechanism is stereo specific. And also take care of one thing. This carbon you have written, it's like this. It is actually a 3-membered ring. Like this also they write on the product simply. So this can be both this one or this one. Yes or no? Right. That is also you must take care of. Okay, write down the product in these reactions. Number of product also you tell me. Try all these. Number of product. Did you write the product, Ruchik?
Yes, sir.
Okay. So CHCl3 gives you singlet carbene. CHCl3 gives you singlet carbene, and singlet carbene, the mechanism is stereo specific. Cis gives cis, trans gives trans, and the only product in the first case is this. This is the product we get. If you talk about the other reaction with CH2N2, it gives you cis as well as trans because the carbene is triplet here. This one and this one. Is it right?
So an extra line in the second column.
One second, Richard. Yes, tell me.
So in the second product, it's ethyl group. You have to draw an extra line. No, sir. Like in the first question only, the for CH2N2, you have to draw an extra line. So we missed it.
Yes, sir, the trans product.
Acha, one more, yeah. Methyl we have.
So
Is this
not
correct?
including stereoisomers. No?
No, just number of products that we are getting
Okay.
here. Stereoisomers means cis and trans we have to consider. Optical activity we are not considering.
Okay.
Just geometrical we'll see. Is this correct?
Yes, sir.
And in this one we get only one product. Why? Could you tell me? It is not
Because
true
geometric
because
law.
it's not
There's no
possible.
H.
No GI.
There is no cis.
This itself is not cis or trans. How can we define cis and trans here?
So if there are no geometric isomers, so how can we write the product?
We can write this product. No, product will be formed, but since no GI means what? The two different structures are not possible. But with whatever structure we can draw for this, with respect to that, we can write down the product of the reaction. Molecule is there, reaction it shows, but it won't give you two different products. Only one product will get you. Hence,
Okay,
we
sir.
cannot define here cis and trans. Okay. CHCl3KOH, it gives you only one product, and that is this CHCl3. So we have chlorine here like this.
Yes, okay, got that.
In this one, both the double bond, the reaction takes place there, and we get this. Correct.
There's only one product.
Only one product. Because again, for the both, here you see 2H and 2S, no GI possible. If geometrical isomerism is there for the reactant, then only we can have cis and trans, no?
Yes.
Here also, the product would be chlorine, 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 chlorine. Is it correct?
Yes, sir.
Yes.
So it can be on the same side also, right? It's the same product.
That also you can do. Same side also you can do. Done, all of you?
Yes.
So isn't it supposed to be on the same side?
Any side you can draw. It's not stereo specific, like, you know, CHCl3 is stereo specific, the reaction is. But here also you see the carbon has CH2. So across this double bond, we have no GI. Across this double bond, we have no GI. So any side you see, it is the same molecules.
Yes, sir.
It won't change. Write down the product in this reaction. We can heat this also slightly. Find out A, B, and C. Okay.
You're done.
Done. So here the product would be what?
So
Like
just
a
Cl beer.
yeah, cyclopentane with Cl and beer.
Correct.
Yes.
Yes, sir.
What about this one? What is A?
It will be like 2 BRs on the side.
Correct. And when this reacts with RLI, what we get? We get again another carbene here. This is B. And then this reacts with alkene. Could you tell me the product now? Did you understand B?
So can you explain
sir.
that? I didn't understand.
See, it's simple. You take one carbon atom which has two Br atom and two CS3. Then what you will do? Suppose I'll take this question. Carbon with Br, Br, CS3 and CS3 with R minus Li plus. What is your answer? Tell me.
So it'll just be 2CH3 with carbene with 2CH2.
Yes, sir.
Carbon with 2CH3.
Yes,
Same thing we have here. Instead of 2CS3, we have this group present and 2Br as it is.
okay, sir. Got it.
Got it? So now you tell me what is C.
So why is B a doublet carbene? So shouldn't it be singlet only?
Why singlet?
So with RLI we formed singlet carbenes.
But there won't be back bonding here, no?
So back
It'll
bonding
convert to a
that's
twisted.
Oh, okay, yeah, okay, sir.
Okay.
So C will be like one more triangle and then methyl.
Yeah, it's pretty
Yes.
complex.
So that will be in between. You will have a spiro compound. Yeah, kind of spiro compound. You will get, yes.
Bicycle.
No, the smaller ring I'm talking about. Is it bicycle or spiro?
No,
I
so
think it's
the big one.
like this. You will getting.
Yeah, there's one spiro and one bicycle.
Yeah, this one is a spiro, and you will get trans also for this. Like this, two product we get. Yes, this two methyl group. This is cis, right? And it is triplet. So we can get cis trans both here. So one is cis, one is trans. Clear?
Yes, sir.
So you see the reaction is something else, but in between the reaction, the intermediate forms by those reactions, those four reactions that we have discussed under the formation of carbene. Okay, so you must remember the reagent which is there or required for the reaction or for the formation of carbenes. Okay, then only you will have the idea of it. Okay, so this is the first reaction, that is addition on alkene. The last one we'll see Simon-Smith reaction. It is actually the same reaction, but the only thing, only the reagent is different over there. We'll use zinc metal over there, okay, instead of heating it. So that's the reaction we have. I'll show you the reaction in the last, but it is exactly the same reaction. Okay, the second reaction we have, write down. We'll do Riemer-Tiemann reaction. Riemer-Tiemann reaction. Riemer-Tiemann reaction is the reaction of phenol, OH on the ring, and this reacts with CHCl3 with KOH.
Hello.
So his Wi-Fi went up.
Did we finish Riemer-Tiemann and phenols?
No, I think he told you.
No,
to
we didn't do
finish.
it. Yeah.
Hello.
Yes.
Yes, sir.
Yes, sir.
Disconnected actually. Anyways, so it is a reaction of phenol with chloroform in basic medium, and I'm taking KOH for this purpose. So again, you see this reagent gives you what?
Singlet carbene.
Singlet carbene, right? The product of this reaction is this. We call it as salicylaldehyde. OH here, CHO at ortho position, and OH on the top, CHO at para position. This one is more stable, the major product here, right? Because of stability due to hydrogen bonding. Okay. Now, the mechanism here you see, it is again electrophilic aromatic substitution reaction. This gives you CCl2 singlet carbene, and this reacts with the benzene. This is the phenol here. This converts into OH, CCl2, lone pair, H, and we have a positive charge here. Okay, then what happens? This hydrogen leaves this bond pair of electron, comes out, and this H plus is taken up by this CCl2 atom that we have here, right? So we have here the negative sign also because it accepts the lone pair, so negative sign. Then H plus comes out, and the product we get is the benzene ring with OH on the top, and we have here CHCl2. Okay, now the medium is basic, right? So basic medium, we have OH. This OH minus attacks onto this carbon atom, and one of the chlorine atom goes out as a leaving group. We have two chlorine. It attacks one of the chlorine atom, goes out as a leaving group, and OH get attached with the carbon. OH, then CH, OH, Cl. Next, this forms a pi. This goes out as a leaving group, and then H plus comes out from this also. It forms OH on the top and CHO here. Same mechanism we have when this CCl2 attached at para position.
So did the hydrogen shift from the benzene ring onto the CCl2?
Yes, yes. Proton exchange.
Okay. That's right.
And this attack of this electron pair here, this step is the RDS of the reaction. Okay, so more tendency for this to donate electron, more will be the rate of the reaction. Done?
Yes, sir.
Okay. This is Riemann Tiemann. It's a name reaction, important. Okay, and simple. You won't get any variations into this. Okay, they may probably ask you which one has more rate of reaction in Riemann Tiemann. Okay, so two things you can understand. One is electron donating nature of this phenol. Another one is is the electron accepting tendency of this carbene, right? So if it is more stable, then its electron accepting tendency will be less, and rate of reaction will be less. Okay, that we can understand. More stable means what? Suppose we have two carbene. One is Cl, Cl, vacant orbital lone pair. One is Br, Br, vacant orbital lone pair. So in this two, which one is more stable?
So the CL1 is more stable.
Sorry?
The CL1.
Why Cl1?
Yes, the C.
So BR is very big.
Because
The extent of back bonding in CL is more.
I didn't get any one of you.
So CL shows more back bonding than BR.
Why?
So we learned in chemical bonding. So I think it was because of BR is bigger than CL, something like that.
Yes, that's right. That's right. See, here carbon is 2p and chlorine is 3p. So 2p, 3p overlap is quite possible in comparison to 2p, 4p overlap, right? That's why the overlap here, we have a better overlap. Hence the bonding is there. Back bonding is possible, right?
I think
That's
something
why
like 2p, 4p, the energy difference is more.
energy difference we don't say. We actually, it's more about the difference in size of the p orbital. One is bigger size, a smaller size. The overlapping is not that good, right? If the size is comparable like this, then the overlapping is better and bond forms the stronger bond, right?
Okay.
So that's why we have 2p, 3p. However, the overlapping tendency is best in 2p, 2p, then 2p, 3p, and then 2p, 4p. That's why here the electron donating tendency is more. So Cl1 is more stable than Br1, right? So if you have two different carbenes here, then the rate of the reaction will be more with the help in the case of CBr2 in comparison to CCl2, because this one is more stable. It has less tendency to accept the electron. Are you getting it? Yes.
Yes.
Correct. So on this particular concept, they haven't asked question in Riemer-Tiemann reaction. But in the other reaction, we'll discuss this, the same concept we have, and they have asked question on this. That is the rate of the reaction, comparison of the rate of the reaction. Okay. So if they ask this thing, you can keep in mind. Otherwise, the reaction is simple. They won't have any change into this one. Correct. Now, this is the simple one, Riemer-Tiemann reaction. So we have some miscellaneous Riemer-Tiemann reaction in which we get unexpected product, which, if you do not see these reactions in the exam, you won't get it definitely. Okay, because the product that we are getting here, you will see you won't expect it at all, right? So you see this reaction, heading you write on miscellaneous Riemer-Tiemann reaction. This reaction is not for NEET. Okay, it's not for JEE Mains also. Maybe in JEE Advanced, this kind of question they can ask. Okay, suppose we have this molecule and this reacts with CHCl3 chloroform with KOH. Chloroform with KOH. And the product that we get here is chlorobenzene. This product we get. Okay, this is miscellaneous Riemer-Tiemann reaction. I'll show you how this reaction goes. First of all, you see this is the 5-membered ring with 2 double bond. is this hydrogen is active hydrogen? Yes?
Yes, sir, because conjugate base is aromatic.
Conjugate base is aromatic, right? So it can easily lose this H plus ion, right? And since the medium is basic, so this basic medium will take this H plus easily. Correct? And then the conjugate base that we get here is this, which is aromatic. Hence, it is a good, uh, acid, good acid we can say, or this hydrogen we can say it is active hydrogen. Okay, now this is the conjugate base we get. Now this reacts with the pi bond here. This reacts with the carbene, dichlorocarbene, that forms with the reagent given in the reaction. Okay, so this, it donates this electron to this, and we have a double bond, so we know we get a 3-membered ring. So I'm not going to, yeah.
So won't the electron pair have a tendency to go towards the vacant orbital?
See, always pi electrons means pi bond has more nucleophilicity than lone pair of electrons. That's why you must have seen some question where you have pi bond and OH. The reaction takes place at pi bond, not on OH first.
Yeah.
Okay, that's why we have this.
Okay.
So this is the reaction we have now. You see, this double bond is just, you consider this as an alkene. Reaction of alkene with this, what it forms? It forms a 3-membered ring with 2 chlorine atom. Clear? No doubt in this. And everything will be, every other thing will be as it is. Negative charge here, I forgot to write. Yes? No doubt?
Yes.
Tell me, is that a simple one? The first reaction you see, addition on alkene. Okay. Next, what happens? Now you see, we'll just number this to make you understand. I'll just number this 1, 2, 3, 4, 5, and 6. What happens? This lone pair, it comes over here and forms a pi bond. This comes over here and forms a pi bond. And this sigma bond, it breaks and it comes onto the 6th atom. Because anyways, the ring is 3-membered, so it is not that stable. So obviously, when it forms a pi bond here, this ring has to break. You have to break this ring, right? So this bond comes over here. Now what happens, you see, if this bond breaks, this entire thing converts into a 6-membered ring. So I'll just draw a 6-membered ring here. And on the first carbon, we have 2 chlorine attached. Suppose this is the first carbon we have. So first carbon has 2 chlorine, right? Then we have second, third, fourth, fifth, and sixth. If this comes over here, we'll have a double bond between second and third carbon. Yes or no? So we'll have a double bond between second and third carbon. We have a double bond between fourth and fifth already present. And on the 6th carbon, what we have? On the 6th carbon, we have a lone pair of electron. Right. Now, after this, what happens if this lone pair, because obviously the ring has tendency to get aromatic behavior here, this lone pair comes over here and forms a pi bond, and the leaving group Cl minus goes out from this. This converts into chlorobenzene. So these are miscellaneous reactions. If you haven't seen it, you won't do it in the exam. It's very difficult to think of these kind of reactions. Understood this? Copied?
Wait, sir, just one.
Done. Okay, now you see, based on this concept, very simple questions they may frame here. Okay, the first one you see, we have a 5-member ring, and this kind of reaction is possible with 5-member ring only. Why, could you tell me?
So only then the conjugate base will be aromatic.
Aromatic. So in all those compounds where the conjugate base is getting extra stability, like aromaticity, in those cases only this kind of reactions observes, right? So mainly we have 5-member ring. You'll get CHCl Br2 and KOH, and one more we have in which we have a change like a 6-member ring, and with this we have a 5-member ring attached like this. CHF2Cl and a base KOH. Okay, simple one. The strongest bond, carbon halogen strongest bond will have over here, right? So fluorine. Between Cl and Br, chlorine is stronger, right? So we have chlorine here. Again, fluorine is there. So we have, so second, we have this, and this 5-member also converts into 6-member, and we have fluorine.
So how do we know where to attach the fluorine in the last example?
You can draw the mechanism. Try this once. Draw the mechanism of it. You'll get it.
Okay.
I think you'll get there only, but you just cross-check once. Do it now. You remove this H from here. You'll get OH, and this double bond reacts with this carbene, and then ring expansion. Means the 3-member ring, you just break down that. Are you doing it?
Yes, so 1 minute, sir.
Okay, try. Okay, done. I think definitely you will have a carbon atom here. So this and this two position you won't get. Only one position is left there. Then. Either you place this fluorine here or here, you'll get the same thing. See, we'll get a lone pair here, and this carbon will be the second carbon. This is fine. You'll get there here only if you do this. This one forms this comes over here, and this carbon, you see this one, and this second carbon will have one fluorine. One more thing, you see, however, we should not take a fluorine here because carbon-fluorine bond is difficult to break. So here you see what happens when it forms a 6-membered ring, and then this lone pair converts into pi. Then in the last one, fluorine goes out as a leaving group. That's what you have done if you have done the mechanism, right? But carbon-fluorine bond, fluorine is not a good leaving group. So usually we should not take, but here we do not have any other choice. If you have questions like this, you have to go with this only. Right, for the reaction purpose, we should not take fluorine here, like I've given here, right? Fine, so these are the reactions, you may have in miscellaneous Riemer reaction, must remember this. Okay, third reaction that we have is Carbyl amine reaction. Very important reaction, this one. It is there in amines chapter, okay? Nitrogen containing compound, amines chapter, it is there. And it is the test of amine. We can differentiate primary amine from secondary and tertiary amine. Okay, so this reaction again we won't do. So write down the heading Carbyl amine reaction. Write down. It is the reaction of primary amines. It is the reaction of primary amines. Secondary and tertiary amine does not give this reaction. Secondary and tertiary amine does not give this reaction. And hence, we can differentiate primary amines from secondary or tertiary amines.
So can you repeat it?
Yes. This is given by only primary amines. Write down secondary and tertiary amine does not give this reaction. Secondary or tertiary amine does not give this reaction. And hence we can differentiate primary amines from secondary or tertiary amines. Right. So one very common question in this that they ask in exam, in all the exams they have asked, they'll give you 4 options and they'll give you which of these compounds shows Carbyl amine test or Carbyl amine reaction. So it is always primary amines. Okay, don't forget it. Now what happens in this reaction? Okay, since primary amines give this reaction, So we'll see the reaction of that only. RNH2 in presence of CHCl3 and KOH. See, this reagent is again a carbene formation. Okay, so this is what you have to keep in mind. CHCl3 KOH, it gives you isocyanide, which has a foul smell, which confirms the primary amine into this. Isocyanide, foul smell, confirms the primary amine into this. We also see the mechanism here, and with mechanism you will understand right. So in the with the mechanism you will understand that why secondary and tertiary amine does not show this reaction or show this test, right? So this is also the test of amines, carbylamine reaction. Okay, so what happens again, you see this forms dichlorocarbene singlet, and NH2 RNH2 as lone pair. So this donates this lone pair into this to this dichlorocarbene, and that this reaction is the RDS of the reaction, and the product here we get is RNC, then we have chlorine, chlorine, lone pair, negative charge, 2 hydrogen, hydrogen, positive charge. Okay. Now after this we have proton exchange. To stabilize the positive charge on nitrogen, one of the H plus comes out and it attached with this carbon atom. Proton exchange. Okay. So this we can write R N H lone pair CH Cl and Cl. Okay. Next step. This lone pair forms a pi bond here, and this chlorine goes out as a leaving group. R N double bond CHCl H and positive charge. Okay. Next, what happens?
Sir, again, proton exchange. That will be possible.
Next, what happens? You see, this H plus, obviously, this nitrogen positive charge, you have to stabilize this. Medium is basic we have. So this basic medium takes this H plus, and it forms R N lone pair double bond CHCl, and then this lone pair again converts into pi, and this Cl goes out as a leaving group. So RN triple bond CH positive charge. Right, and then what happens? Medium is basic, so the basic medium sp hybridized carbon atom, electronegative, right? This hydrogen is acidic. It takes this H acid-base reaction. It converts into R N triple bond C lone pair negative positive charge. This is isocyanide, okay, which we also write it as this one, R N double bond C and a coordinate bond like this. Isocyanide it forms. So again, so all these reactions, the mechanism is not important. You should just memorize the property. Okay, like I said, it is given by 1 degree amine. Okay, that you should memorize, because mechanism based question they won't ask. It is not possible to frame any mechanism based question over here. Okay. One more very important comparison here, which I have already done, but I'll just highlight here. The RDS of the reaction is what? The RDS is this, right? So again, you see the rate is directly proportional to the electron donating tendency of this amine and electron accepting tendency of this carbene. Yes, and when carbene accepts electron easily, when it is less stable or more stable?
Less stable.
Less stable.
When it is less stable. So the rate of the reaction is directly proportional to the electron donating capacity of amines and inversely proportional to the stability of carbene. Can we say that? Right? So this relation you write down, rate of reaction ROR is directly proportional to the electron donating capacity of amine and inversely proportional to the stability of carbene. Copy this down. Done. In terms of rate of reaction, if you see, the same kind of concept we have, like we have in Riemer Tiemann reaction, Varun. Because both has the same rate of RDS. Okay, yes. So one more thing you see, like the one thing that I told you, why secondary and tertiary carbon does not show this reaction, tertiary amines does not show this reaction. Because you see, we have two times, one is this proton exchange and one is this base takes this hydrogen, which is attached to the nitrogen atom here. So if it is, suppose, if it is what we say, secondary amine means the hydrogen has one R group present here. So here also we have one R group. This reaction possible. Here also we have one R group. But here, when it comes to this point, this base won't take this R. Right. So basically, because of two R group, this N plus is not getting stable. Hence, this reaction itself is not possible. That's why we won't get isocyanide here. If it is tertiary, then this proton exchange is only not possible. Hence, the reaction is not possible. That's why primary and secondary amines does not show this reaction. Clear? Understood? See, they can ask you this question. I'll just go to the next page and compare the rate of the reaction here.
So could you go to the last page, just 1 second?
Just a second. Yeah.
Yes, sir.
One more I'll just give you. Okay. So here we have it is in resonance with the ring. Electron donating capacity is less. Rate of the reaction is more for this compound. Again, this one is in resonance with this pi bond. Electron donating capacity is more over here. This one and this one, if you compare,
180.
first one is more. Electron donating capacity. This one, if you see, it is plus m minus m plus h. So this is 1, this is 2, and this is 3, the rate of the reaction. Got it?
Yes, sir.
Okay, so all of you have answered. You see how many primary amines in these molecules I have given. Do we all have primary amines in this? We all have, yes. Is this primary amine? Yes, no. Correct.
Yes, sir.
Yes,
Yes,
sir.
sir.
What happens if I give you this particular question? NCH3, HCH3, and CH3, NH2. What happens in this two?
No, sir, that the one with CH.
Only that second one will do
Second one.
Second one will
reaction.
Yeah,
Yeah,
react.
first
second
one
one
won't
will
react.
react.
Won't react.
First one won't
Secondary
react.
amine.
Yes, sir.
Only the second one, right? So this won't react. Only this one, right? But first step is possible here, you see. From here to here, till here it is possible. Is it possible? This is not possible. Since this one is not getting stable, right? If it forms also, this will go into the backward direction and will get the initial molecule. That's why we don't even consider, in some book like I have seen, that they compare this particular, they like say that okay, this step is possible, after this it is not possible. So we can compare the rate till here. But actually the carbyl amine reaction is still here, isocyanide formation. So the reaction is not possible at all. If this forms also, then also it has very high tendency to go into the backward direction because the positive charge on nitrogen, it is not getting stable. If it is secondary amine, then this one is stable, it forms still here. That's what the case I have taken. If it is tertiary, then this won't form, it will go back. If it is secondary, then this will form. This protons, this H plus will go over here, will get here. In case of secondary, after this one, the step is not possible. But still we do not compare this because the carbyl amine reaction, again, it is still here, the formation of isocyanide. So if they ask you to compare the carbyl amine reaction, you have to consider only those compounds which are forming the final product, that is isocyanide. Common one, but just take care of this thing. Okay. If they specifically mentioned that 3 compounds they have given, primary, secondary, and tertiary, correct? And if they ask you that compare the rate of the first reaction in carbyl amine, then probably you can think of that, the electron donating capacity, because the first reaction is taking place for secondary and primary, right? Not for tertiary. So you can compare primary and secondary over there. But this kind of confusion they won't create. I haven't seen this kind of question, but maybe I have just given you an idea. If they have mentioned the first step only, the RDS only, then you can compare the primary and secondary, not tertiary in that case. Anyways, so the next reaction we have, fourth one, right? Is it fourth one?
Yes.
Yes, sir.
The fourth one is Arndt Eistert reaction. This is the reaction of acid, carboxylic acid chapter, it is given in that.
So can we take a break before this?
Chalo, break.
Thank you, sir.
6:21. We'll start at 6:40, okay?
Yes, sir.
Okay. Hello.
Yes, sir.
Yes. Shall we start? Okay. Arndt Eistert reaction. It is a reaction of acid, double bond O, OH. And the reagent that we use in this reaction, the first one is SOCl2. The second one is CH2N2. Third one is silver oxide. We use this as a base here. And we use aqueous basic medium here. Okay. We can also use here can also take RO minus and the conjugate acid of this as a solvent, that is ROH. Alcohol also we can take. And the product we get here is RCH2 C double bond O OH. Insertion of methylene group, that is it. Between the carbonyl group and the alkyl group, one CH2 you have to insert, that is it. So we are getting higher acid into this, right? Number of carbon atom increases in this reaction.
So what is that Eistert? Is it Eistert or Eistert?
Sorry?
So what is the EIST one?
Your voice is not coming properly, Ruchin. A bit louder. Come again.
So what is the EIST? What is that spelling? I can't read it.
EISTERT. Eistert reaction. EISTERT. Okay. Now, see this reaction. The first step is the reaction of acid RC double bond OOH with SOCl2. And we have done this reaction, okay? SOCl2 gives you what? Acyl chloride, RC double bond OCl, plus we'll get SO2 gas. HCl also eliminates in gaseous form. Okay. This RCOCl reacts with diazomethane in the next step. C double bond OCl plus CH2 single bond N triple bond N, lone pair positive charge, lone pair negative charge. Okay, this attacks onto this carbonyl carbon and this pi electron goes up, and when it comes down to form a pi bond, then this chlorine goes out as a leaving. So directly I have written this. So it forms R C double bond O CH2 positive charge, N triple bond N positive charge. Okay, now the next step is the reaction of base, that is Ag2O here. Okay, so we have this RC double bond O CH N triple bond N positive charge, positive charge. Ag2O behaves as a base here. This O lone pair of electron takes this H plus and it converts into RC double bond O, CH, CH with lone pair and triple bond N, positive charge, plus Ag2O H plus, and from this Ag plus comes out. This Cl minus combines with Ag plus and forms this AgOH and AgCl. This is one part of it. Okay.
Sir, in the second step, how does the carbon also have a plus charge? I didn't get that.
Just a second. I'm just checking that. H plus it will take. We'll have a lone pair. Then we have CH and negative charge. Yes, tell me what?
So the second step, sir, when it was acid chloride, and then how does the carbon, the CH2 plus, how is there a plus charge still there? So it was a minus charge, right?
Is it this one is minus charge, not plus?
So
See,
the next after that it becomes plus.
Oh, this one.
Yeah.
This carbon donates its electron, no? Achha, just a second. It donates its electron, and this goes away, right? So carbon has 4 bonds. We don't have any charge here.
So that should be neutral.
Yeah, it's a neutral charge. 4 bond we have here, no? We don't have any charge. Okay. Diazomethane, you see, I have written here the resonating structure of it. Okay. But the structure of diazomethane is this. I have given you this in the preparation of carbene. This is the structure of diazomethane, positive charge. Okay. And when you draw the resonating structure here, you'll get this one. So I'm using resonating structure here directly. Okay, here also we don't have plus. Then only this base takes H plus and we have a lone pair negative charge. Okay. Now, this is what we get. Next is we have Ag2O, and when we heat this next, okay, since we're heating this Ag2 and we're heating this, so when we heat this, then what happens? Nitrogen evolves, right? N2 goes out from this, and we get here R C double bond O CH lone pair and a vacant orbital. Now, what is this carbon?
Carbene.
This is carbene, right? So this reaction, this intermediate here, it carbene forms. Okay, so carbene forms here when this, see, we haven't discussed this in that 4 reaction because it comes under diazomethane only. But when diazomethane reacts with acyl chloride, then carbene forms like this. Okay. Now, here we have an important rearrangement. All of you have copied this? One note you write down. Whenever a carbene forms, adjacent to the carbonyl group, whenever carbene forms adjacent to the carbene group, carbon, then Wolff rearrangement takes place. WOLF, Wolff rearrangement. Whenever carbene forms adjacent to the carbonyl group, I just said it wrong last time, I guess. Whenever carbene forms adjacent to the carbonyl group, then Wolff rearrangement takes place. This you don't write this. I'm just telling you. This is Wolff rearrangement. I'll show you what is Wolff rearrangement. But this Wolff rearrangement is possible with nitrines also. Nitrines is again the another intermediate that we'll discuss in nitrogen containing compound chapter. Okay. So what is Wolff rearrangement? We have this carbene, that is R, C double bond O, CH, lone pair vacant orbital. So when it goes under Wolff rearrangement, this alkyl group, it takes this bond pair of electron and rearrange itself onto this carbon. This is Wolff rearrangement. When it comes over here, this lone pair converts into pi here, and it forms RCH double bond C double bond O. Okay, one very important property here, when it goes under Wolff rearrangement, the configuration of R won't change. Write down this. On the basis of this, they have asked question in the exam. It goes under Wolff rearrangement and configuration of R won't change. What do you mean by this? See, this R can be chiral also. It has R or S configuration possible. If it is chiral, then this case we have. So whatever the configuration we have here, the same configuration we have here also. That configuration won't change. Clear?
Yes, sir.
This is very important. You must remember this. So this is Wolff rearrangement possible when carbene or nitrine forms adjacent to the carbonyl carbon. Okay. Now the next step is the base, that is OH minus. In carbene, you have not framed your doubt properly, Varun. Would resonance also be possible in carbene? Carbene may take part in resonance. That's why we have back bonding there. No, back bonding is a type of resonance only. Right. So carbene can take part in resonance, provided the condition is there. Okay. So last step you see we have OH minus H2O, the last step, right? OH minus H2O, the base that we have here. Now this base attacks onto this carbon atom, and this pi electron is shift onto this carbon. Okay. In some book, what they do, they have, you can consider that like this also. If this comes over here, this pi electron goes over here. When it comes back, then this pi electron shift over here, right? So we get here RCH C double bond OOH. After this, we have two possibilities. Means you can consider any one. Simply, you can take with H2O, it protonates and forms water and forms RCH2, C double bond OOH. Or the another possibility is what? That this goes under proton exchange. Any one you can write. Okay, both you do not write. Proton exchange. This H plus rearrange itself over here, and it forms RCH2, C double bond O minus, and this protonates with water, converts into RCH2, COOH. Both way you can do this. This step, the second one that I have written, proton exchange one, this one is more, acceptable. Why? That also I can tell you. See, we have two acidic group, you can say, acid and water, right? So if this C minus, we have acid already present, then this C minus will take H plus from this acid. That's why this proton exchange will give you this. And then this is a strong base. It can take, H plus from this water. Now the water is behaving as an acid here. Right here, what I have written, that this takes H plus from this, which is not technically correct that much. But in some book, you'll see this kind of mechanism also, because eventually we are getting the same product. But actually, it goes this way. Okay, so if you want, you can write this one, but this one is the more appropriate mechanism we have. Okay. So all these things you don't have to do. This complex mechanism you don't have to draw in the exam. What you need to understand here, that if you have this molecule, suppose carbon has D, and here we have H, this is CH3 with C double bond OOH. It reacts with SOCl2, then CH2N2, and then we have what, Ag2O base. We are heating this so that nitrogen goes out, and we have the last one, OH minus H2. With all this, just reagent you keep in mind, the product would be CCH2 C double bond O OH. And this thing, since the configuration won't change, so this thing will be as it is, CH3. Sometimes in the option, what they do, they'll change the position of this, HCH3 or DH like this. So again, we have same thing, odd number of exchange, even number of exchange you can keep in mind. So if it is R, for example, if we are assuming this as R, this would be R only. The configuration won't change. This is the important property of Wolff rearrangement we have.
So,
yeah.
So that extra carbon we are getting, the two hydrogens, one will depend on CH2N2 and one will depend on OH minus, right?
Solvent, you can say, not OH minus, whatever solvent we are using.
Yeah, solvent.
Right.
Okay.
Clear? Okay. The next reaction is acid-base reaction. Acid-base reaction. Just a second, I'll read. This one. Acha, one thing I forgot to tell you. Oh no, this is fine. This is fine. Correct. We'll discuss that one later. Done, Advik? Okay. So the next reaction is acid-base reaction. Sorry. Acid-base reaction is possible with molecule which has active hydrogen. Write down. Possible with molecule which has active hydrogen. Okay, active hydrogen, you know, hydrogen attached with electronegative element like OH, HF, HCl, HS, all those. Very simple reaction. You see this. Suppose you have an alcohol ROH, and if this is allowed to react with diazomethane or ketenes, and we heat this. This converts into ROCH2H. This is the molecule. Insertion of methylene group between oxygen and hydrogen. Okay, insertion of methylene group between oxygen and hydrogen. One thing is very important to observe here. This was an alcohol, and we get an ether by this reaction. However, these two are not isomers of each other, but one functional group converts into another. Okay, so just you have to insert this CH2 between O and H, more electronegative element and less electronegative element.
So,
Yeah.
So what do you mean by active hydrogen?
Active hydrogen is all those groups in which the hydrogen atom is attached with electronegative element like oxygen, nitrogen, fluorine, chlorine, sulfur, all this. Like water has an active hydrogen. Alcohol has an active hydrogen. NH3, the hydrogen is active hydrogen. Got it?
Yes, sir. Thank you, sir.
Acidic hydrogen basically. Or you can also take sp3 hybridized carbon. This hydrogen is also active hydrogen, which comes out into the solution as H plus easily.
Yes, sir.
Okay, so this is the reaction we have. Okay, mechanism, just two line we have into this one. CH2N2, we know it gives what carbene here we get here.
It will be 2 H's.
We'll get singlet or triplet here. CH2N2.
Triplet.
No, we'll get singlet. Why singlet? Polar solvent, na? Lone pair. See this? Yes.
Yes, sir. So
That's why we get
triplet is only in non-polar. Then.
Non-polar. So this can stabilize this. This can donate its lone pair into this, and singlet is stable here. That's why we get singlet. Okay. So we get singlet carbene, and then the alcohol lone pair, it donates into this. So what we get here, you see, we get ROCH2. Okay, H here, positive charge. And this CH2, one lone pair we already have, and another one we get from this oxygen. So here we have the negative charge. Just a second, we have one here, one is there in the orbital. So one we won't show. This won't be show because it is there in this bond, no? 2 electron is already here. We don't have to show this. Fine. Next, what happens? Could you tell me?
Proton exchange.
Proton exchange. See, proton exchange you say, or you say this H plus comes out to stabilize this. Both are the same thing. It goes into the solution, and from solution, this CH2 minus will take that H plus. So it's other way, just we are saying. So we'll get here ROCH2H. That is it. So alcohol converts into ether, but molecular mass is more here. They are not isomers of each other, but one functional group converts into another. Similarly, if you take acid, what we get here? If you take acid, suppose I'll give you this example, RCH2, ester, right? So again, you see functional group is getting changed, right? C double bond O, OH, simple one, CH2N2, and you heat this, you'll get CH3, CH2, C double bond O, O, CH2H. This is the molecule, ester. Okay, phenol. OH with CH2, N2. This is suppose carbon 40, just for the reference. O, and then what we get? Sorry. We get O, CH2, 14, and H. No doubt in this. HF converts into? HF converts into?
So CH3OH.
HF.
So CH3
HF converts into CS3F. Okay, just H and F, CS2 you have to insert. Okay. Okay, so this is acid-base reaction, insertion of CS2. So in the last reaction also you see Arndt Eistert reaction, insertion of CH2, and here also we have insertion of CH2. Okay. Now the next one, sixth reaction, sixth one. Reaction on carbonyl compound. Reaction on carbonyl compound. See, we have a carbonyl compound, double bond O, and when it is allowed to react with diisomethane, CH2N2, this gives you two products here. One is this, and another one is this. Double bond O. This one is KCP and this one is TCP. These two products we get here. Okay. Now look at the mechanism, how this reaction proceeds. This is the molecule we have. We have CH2, lone pair negative, single bond N, triple bond N, positive. Okay. So in the first step, this negative charge, it attacks onto this carbon atom, carbonyl carbon, and this pi electron shift on to the oxygen. So it converts into this O minus, and here we have CH2 and triple bond N, positive charge on it. Okay. Now, when you heat this, N2 goes out from here. O minus, and here we get CH2, a vacant orbital on it, plus N2. Then this O donates its electron into the vacant orbital of it, and it converts into this molecule, O and CH2. This is one molecule, this is one of the product here, and this is KCP. It is fast forming, and KCP of the reaction not that stable. Anyway, 3-membered ring is forming, so it is not that stable. Another possibility from this is what? Either you see, either this oxygen donates its lone pair into the vacant orbital of it, or this lone pair may come over here. You copy this down, I'll show you the next mechanism. How do we get this product here?
So shouldn't there be a positive charge on the CH2 here?
Where?
So in the second half step, so just before we form it.
This one?
Yes, sir. Up from this step to the next step, won't we get a positive charge on CH2?
This one here.
So the one before that, instead of forming the carbene, because
Give
the
us some positive
nitrogen
charge.
took the lone pair. Yes, sir.
So 1, 2, 3. We're not getting carbene here exactly. Just a second. We should have one lone pair on this. Correct. So we'll have one positive charge here, and it is not a carbene here, you see. This part, here we are not getting a carbene because carbon has 3 bonds here. Is it? This one is not a carbene here. But the reaction is similar. Okay, reaction is similar. That's why we are discussing it here. Carbene, it is not forming. One more possibility is what? That if this lone pair, if it comes over here, then one of the alkyl group that comes out, right, will push this alkyl group out. However, this bond is difficult to break. And since we are heating it, so we can consider this, right? So one of the alkyl group, the sigma bond breaks, and this alkyl group rearrange itself onto this because it has one vacant orbital. Correct. So what happens in the next step, you see, that we have this. CH2 vacant orbital. Okay, and here we have O minus positive charge. If this comes back here, so one of the alkyl group comes out, right? And this rearrange itself onto this carbon. Which one we'll talk about that, okay, later. I'll tell you which one will come out, either this one or this one, because it is unsymmetrical. So this one, we have double bond O, and this CH2 is here, and with this CH2, the alkyl group is attached. So this product is the TCP of the reaction, thermodynamically controlled product, more stable. The group that migrates here, right, that depends upon its migratory aptitude. Okay, and we know the migratory aptitude, we have 2 different orders. We have hydrogen is the best migrator, then we have pH, and then we have R group, that is CH3, right? If other groups we have, then more electron donating groups are better migrator. Both point you write down. Better electron donors are better migrators. So the one which is a better migrator, that will migrate onto that carbon atom. Okay, this is one of the mechanism. What happens, you can also consider this reaction like this. Why we are doing this here and how carbene formations is possible here. Like this also the reaction proceeds possible. Okay. If you take little bit amount of base here you see, suppose we have this, or if you go one step back, okay, if you want you can copy this down, I'll write down here. Here what happens, we have O minus and here we have CH2 N triple bond N positive charge, correct? Now we'll take a little bit of base here. If you take base also with CH2N2 in basic medium, if you have this, then this base will take this H plus, forms H2O, and it forms O minus, this CH1 lone pair, negative charge, and triple bond N positive charge. Now when you heat this goes out and we get a vacant orbital on the carbon atom. CH lone pair, vacant orbital, and this would be as it is. Now after this donates its electron here and we'll get a 3-membered ring. Still the carbon has one negative charge on it, one lone pair on it, which gets protonates from the water that eliminates in this reaction. Right? So in the last step, it protonates by the water that we have here, and the base concentration is maintained. Similarly, after this comes over here, we'll get double bond O, this CH plus one lone pair on this, it gets protonates from water, forms CH2 over there. That is how we can understand the mechanism. So both way it is correct. Like this is how the carbene formation possible in this reaction. Understood this?
So could you explain how the base attacks the first step?
See, I have discussed one similar mechanism previously. This base will take this H plus from this. Okay, because we have nitrogen here, right? So this H plus, see, nitrogen has positive charge, electron deficient, right? So it will drag the electron pair towards the side. So this hydrogen is also acidic here. Hence, base can take this hydrogen from this, we'll get a lone pair over here. Like this, you can see.
Yes, so got it now. Thank you, sir.
Carbyl amine reaction is a similar thing. This will take this H plus and we'll get here lone pair. Okay, this is how you can understand this. But the point is you'll get KCP, which is a 3-membered ring. Okay, JEE they have asked this question, okay, on both the mechanism, okay, the 3-membered ring wala and this TCP, right? 3-membered ring will get KCP and the open chain is structured like this one is TCP. It depends upon the migratory aptitude of the group attached to the carbonyl carbon. What is the migratory aptitude? It is maximum for hydrogen, then phenyl, and then CS3. If you have electron donors here, not like apart from these three, if you have any other group, then we just compare the electron donating capacity. Better electron donors are better migrators, that is it. This is a reaction on carbonyl carbon. Okay, now look at some example on this. Write down both the product, TCP and KCP, both in this. We have CH3, C double bond O, H with CH2 and 2 hitting. CH3, C double bond O, CH3, same reagent. Oh, wait. Both products we write down. Done? Okay. So the product here is KCP would be, we have CH3, COH plus better migrator is hydrogen. So we have CH3, C double bond O, CH2H. KCP, TCP. This one is CH3, CH3 plus C double bond O, CH2, CH3. This one plus we'll get a 6-membered ring, double bond O. CH3, CO. This is one product. Another one is CH3, C double bond O, CH2, CH3. Phenyl is a beta migrator. pH CO, CH2, CH3 plus pH CH2, C double bond O, CH3. This is the answer for this question. All of you got the same answer?
Yes, sir.
Okay.
Yes, sir.
Now the next
One
reaction
second,
is,
sir.
okay.
Wait, sir, 1 second.
So how do you get in the third one? So how do you get the hexanone as the
See what we are doing in all the reaction. Between C double bond O and carbon, one CH2 we are inserting, right? So we have a 5-member ring. So C double bond O
Expansion.
here will insert CH2.
Oh, okay. Yes.
Okay. Done?
Yes, sir.
Okay. Next reaction is Simon-Smith reaction. It is the reaction of addition on alkenes. Similar reaction we have. It is stereospecific, and we get cis gives cis in this, trans gives trans, like I said in the beginning, right? Write down this stereospecific reaction. And the reagent we use here, C double bond C, it is allowed to react with CH2N2 in presence of zinc. This gives you the same product. We'll get a 3-membered ring here, which is this, CH2. How the reaction proceeds, you see, zinc gives 2 electron and converts into Zn plus 2. Now, in presence of these 2 electron, okay, CH2 I2 here. Okay. This is, we have I2. Only the reagent is different. Okay. Now, in presence of this electron, free electron, thus carbon-halogen bond becomes weak. That we know already, right? So we have CH2 and 2 iodine plus 2 electron. It converts into plus we'll get zinc iodide. Okay. Now this reacts with the alkene. This reacts with the alkene. Carbon has 1 iodine here and H. You can also draw the mechanism similar to this thing, what we say, carbene, right? But if you heat this, then I minus goes out and we get a vacant orbital here. Since we are not heating it, that's why the mechanism I write down this way. Okay. Simon-Smith reaction, we don't heat it. But reaction is possible when you heat this also. Okay. So this lone pair, it comes over here. It comes over here. This pi electron comes over here. And when it attacks onto this carbon, this iodine goes out as a leaving group. Okay. So this converts into C single bond C. And we have here CH2. And Zn combines with iodine here, I minus, forms ZnI2. So only the reagent is different, but pattern of or the mechanism also, it's very much similar. Okay, we are using diiodomethane here, not diazomethane. One important reaction here, you see, not with this one, diazomethane reaction I'll show you. Suppose you have an alkene, CH2. You're taking here CH2N2, the product that we get here, and we are heating this with CH2I2 and zinc. Sorry, just a second. CH2N2, this is it. What is the product we get in 2 reactions? Done. What is the answer? Tell me. See, when you heat with this CH2N2, it forms diisomethane and it converts into cyclopropane. Same reaction when we have done it already. But when we do not heat this, then the product won't be according to the carbene intermediate. Because if you look at the mechanism, CH2N2, it converts into this when you draw the resonating structure for this, N triple bond N and positive charge on it. Then from this, we say that this N2 comes out and we'll get a carbene intermediate, which is this. Right. But when it happens, when you heat this, then only it takes this bond pair of electron and comes out. So if you are not heating it, which is also the case in the previous case, that is Simon-Smith reaction, you're not heating it, so this N2 won't come out into this. And in this case, we'll get a 5-membered ring as the product. How it happens, you see? This lone pair, we can write this as CH2 double bond CH2, and the diisomethane we can write like this: CH2 negative charge, N triple bond N positive charge. This attacks onto this, pi electron shift over here, and this converts into H2C negative, CH2, then we have CH2, then we have N triple bond N, okay, positive charge. Okay, now this lone pair, when it comes over here, this pi electron shift onto this, which is not easily possible because nitrogen already has one lone pair, but this pi bond can shift, and this is the way this N plus gets stability. So it converts into a 5-membered ring in which 2 nitrogen attached with a double bond like this. So we'll get a 5-membered ring here when we are not heating it. Clear? Understood? Okay. The last reaction we have, that is insertion on alkane. Small reaction, there's no mechanism, you can understand like we did the other reaction. When you have alkane, suppose we have CH3, and if you are heating with diisomethane CH2N2, then it converts into CH3, CH2, Okay, if you have CH4, it converts into CH3. If you have CH3, CH2, then the answer is we can have CH3, or we can have a straight chain compound CH3, CH2. So between carbon and hydrogen, this CH2 group get inserted, right?
So
Takes the
most
place
of
of.
these reactions are insertion reactions only, right?
Sorry?
So like most of the reactions that you've done are insertion reactions. only,
Insertion
basically.
means half of the reaction after 4th or 5th one, I think.
Yes.
All are the insertion of CH2. You remember this reaction is there in alkane chapter also, when we get a larger alkane, bigger alkane, CH2 into with this. Okay, so this was the last reaction of carbene and the intermediate, that is carbene. Okay, so this see, we have done the reactions of all the chapters actually. A little bit of alkyl halide, then carbonyl compound, alkene, alkane also, with few reactions we have seen. Okay, so we'll start another topic here, that is aromatic chemistry. A little bit we have already done, like phenols electrophilic aromatic substitution reaction, but we'll see the electrophilic aromatic substitution reaction on benzene. Benzene, all the carbon atoms are equivalent, so anywhere the electrophile get attached. Okay, when it is phenol, then phenol OH group directs the electrophile to attack at ortho and para position. That is the directive influence. We have just seen that. Okay, so based on that only, just we'll see few reactions of benzene, that is the aromatic reactions of benzene, aromatic chemistry. We'll discuss into that. A few more reactions we are left with, and this is done. Okay, we are done with this chapter. After finishing this, you can attempt the questions of aldehyde and ketone also. Only few preparation method we haven't done, and some specific reactions like aldol condensation and Cannizzaro we haven't done. But other reactions like reactions related to Grignard reagent, oxidation reduction, all those reactions we have done. So you can attempt some, almost around 70%, 80% questions of aldehyde ketone. So if you want, you can give it a try. But after finishing this, next class we'll start with aldehyde ketone chapter only. Then we'll do whatever the reactions left into that. Okay, mostly our focus will be on the SN-AE reactions. Okay, nucleophilic substitution, addition elimination reaction, in which we'll talk about all those reactions, condensation reactions, aldol and Cannizzaro. Okay, so let us start with aromatic chemistry. A few like reactions, like I said, we'll discuss this and we'll finish it. Heading, all of you write down aromatic chemistry. Reaction of benzene, basically we'll see. Aromatic chemistry. You will get it easily because we have already discussed it. How the reaction takes place, we know the benzene ring interact with an electrophile. First, it converts into an intermediate cation, which is this, right? And to maintain the aromaticity, H plus comes out and it converts into this. This is what we have discussed in phenol, right? After this, positive charge here. After this, the nucleophile won't attack onto this. The chances are very less. It won't give you this one, because the aromatic, if it happens, then aromaticity is lost here, like permanently, right? That's why this particular reaction is not possible here. 1 second, guys. Okay, so this is the reaction we have. So nucleophilic attack is not possible here because aromaticity, is lost completely here. So that's why it is not possible. So this kind of reaction we have already discussed last. The only difference is when you have phenol, then this electrophile would attack at ortho or para. But here it can attack at any position because all positions are equivalent here, right? Now in this also, benzene also goes under nitration reaction. Okay, exactly similar reaction we have. I'll just quickly write it down so that you can understand it easily. We have reaction of first reaction we write down on the top, nitration. There we use HNO3 with H2SO4, the mixture we use. So here also we use the same thing. benzene, HNO3, H2SO4, it converts into nitrobenzene. Exactly same mechanism, only OH is not present over there. Is the reaction of this also, how do we get electrophile here, NO2 plus? I have already given you, so I'm not writing it down. Right, electrophile is NO2 plus here. Okay, one important thing here, we can take this two for this reaction. We can also take only concentrated HNO3 for this reaction. Means what all reagents we can take that you see. The reagents here, we can take concentrated HNO3 only. Okay, concentrated HNO3. What happens in this? HNO3 plus the another molecule of HNO3, which is this. When it reacts, it forms NO3 minus plus H2O plus NO2 plus. You can understand this reaction easily. H plus OH forms H2O. So it forms NO3 minus and it forms NO2 plus. So this is the electrophile for this reaction. Okay, so basically you see this, it is an acid-base reaction. One is behaving as an acid, other one is behaving as a base. Right, we can also take here N2O4 for this purpose. Right, for example, you see this N2O4 is this, the structure we already know. This is the structure of N2O4. And this converts into NO3 minus and NO2 plus. This comes over here and it forms this. Again, the electrophile is NO2. Similarly, we can also take, rarely, you have these reagents, NO2 plus ClO4 minus. Also, we can take this as. Okay, the electrophile is again NO2 plus here. These are the electrophiles we can take. One reaction that we haven't done in the last class, that is nitrosoursine reaction. We'll discuss after this. First, you copy this down. Okay. Second reaction you write down.
Sir, can you go back to the previous slide?
Just a second. Nitrosoursine, SOATION.
Yes, sir. Done. Thank you.
Done?
Done, sir.
Okay. Nitrosoursine reaction, the reagent we use here, we have benzene ring, and this is allowed to react with NaNO2 in presence of an acid. H2SO4 we can take HCl. The product that we get is N double bond O, right? This is nitrosobenzene. Nitrosobenzene. Okay. How this reaction proceeds, you see the first step, NaNO2 reacts with the acid HCl, H2SO4, whatever you take, I'll write down here. H2SO4, and it converts into Na2SO4 plus nitrous acid, which is HO and double bond O. Nitrous acid. Okay. Now this in presence of acid again, in the second step, H2O goes out and we get nitrosonium ion, that is NO+. This is the electrophile here, nitrosonium ion, one vacant orbital we have here. Nitrosonium ion. Okay, now this again behaves as an electrophile, attack onto the ring, and we'll get this product. Done.
So 1 minute.
Okay. The third reaction is halogenation. Mainly we do this for bromination and chlorination. Bromination and chlorination. The reaction is we have benzene ring, Cl2 AlCl3. It converts into chlorobenzene, HCl forms. This, when reacts with Br2 with FeBr3, see all these behaves as a Lewis acid, right? It takes Cl minus, forms AlCl4 minus, and then Cl plus is the electrophile attacks onto this. Okay, so if you have any doubt, you can stop me anywhere, right? I am assuming that you are understanding all this since we have had a class on this phenol chapter, right? So you can stop me anywhere you want. Okay, so this is the reaction we have. You just have to keep in mind that what all reagents we can use here. Like for chlorination, the other reagents also we can use Cl2 with FeCl3. Chlorination, bromination has very similar, properties. So all reagents we can use for these two, ZnCl2. Chlorine we can also use with another Lewis acid, BF3. We can also use FeNCl2. Because when these two react, it converts into 2 FeCl3. You can balance this reaction. And then with chlorine, Cl2, FeCl3, it converts into FeCl4 minus plus Cl plus, which is an electrophile for this. All these reagents we can use for this purpose, halogenation purpose. Okay. Yes, correct. Friedel graph, similar to that. The same reaction actually. Okay, next reaction you see. This reaction is important. Suppose we have benzene ring. Benzene ring, just now we have syn. It reacts with Cl2.
Go to the previous slide for a second.
With Fe.
Thank you, sir.
One more thing here, iodination reaction is reversible in nature. Only iodination is reversible. All other halogenation reactions are irreversible. Right? Iodination is reversible. All others are irreversible. Like sulfonation is reversible, nitration is irreversible. Okay, Cl2 with Fe, just now we have seen it gives chlorobenzene and the product of the reaction is this. But then this is allowed to react with chlorine, excess of chlorine in presence of H nu. Then it is a free radical reaction, excess of chlorine we have, and we get chlorine at all positions here like this. This free radical, we get chlorine at all positions. Okay, this compound we call it as gammexene, Gammexene. The another name for this one is linden.
So it's a cyclohexane ring. It's a cyclohexane ring.
Yes, yes. Oh, just a second. I think we'll have double bond here. I have written it by mistake actually. Let me correct it here also. Because aromaticity would be there, no? The halogen and hydrogen bond, carbon and hydrogen bond get dissociated here. Right, so this double bond would be as it is, and we'll get here. Gammexene, linden, and the name of this compound, the other name is, it is benzene hexachloride. That also we say. Okay, double bond won't break. So this is the reaction we have. Now the another reaction in this is chloromethylation. CHLORO, chloromethylation.
So this is under halogenation only.
No. It's a different reaction. Halogenation we are done. Reaction of benzene with formaldehyde, HCHO, with HCl, ZnCl2, and it converts into benzene with CH2Cl. How this reaction proceeds? First of all, these two reacts and it converts into H plus and ZnCl3 minus. ZnCl2 is behaving as a Lewis acid here. Okay, this H plus reacts with formaldehyde, H, C double bond OH, and it converts into H, COH, H, and positive charge. You can understand this. This lone pair takes this H plus and pi electron shift over here, will get this. So this is the electrophile we have. Now this reacts with benzene. CH2 OH positive. Electrophile you must remember, okay? In which reaction what electrophile we have? We get CH2 OH plus H plus, right? So this H plus further, it protonates the alcohol and it converts into a carbocation, that is CH2 plus, stable carbocation, and then from Cl minus, from ZnCl3 minus, it attacks as a nucleophile on the carbocation and converts this into CH2Cl. This is chloromethylation. Done?
Yes.
Yes, sir.
See, sulfonation reaction is exactly same here. You'll get SO3H, electrophile is SO3. Okay, nothing difference we have into this one. Okay, two more reaction we have to discuss, the last two reaction here. And that is write down, it is Gutterman, it's a name reaction, Gutterman-Koch reaction. And then other one is Gutterman aldehyde reaction. Both gives us the same product. Only one reagent is different. We'll discuss that. Benzene reacts with carbon monoxide with HCl in presence of AlCl3, and it converts into benzaldehyde, CHO. Okay, HCl is, this one is Lewis acid, it is an acid. So this gives you what? If you look at this mechanism, the first step is HCl with AlCl3. It converts into AlCl4 minus plus H plus. This H plus reacts with carbon monoxide, which is C double bond O, and we have a coordinate bond here. Positive charge, and this one has negative charge with H plus. It converts into carbon, takes this H plus, and it forms CO H positive charge on it. Okay, we have this positive charge, we take this electron and we'll get finally this. Now this is the electrophile for the reaction, which attacks onto the benzene ring and forms benzaldehyde here. Which is this. Same mechanism, H plus goes out, takes Cl minus from this, forms HCl. So Gutterman-Koch reaction, we are using carbon monoxide with HCl AlCl3. Okay, Gutterman aldehyde reaction, instead of CO, carbon monoxide, we are using HCN there. HCN, and in the second step, H plus H2O. You finish this, I'll just show you the next reaction. Done?
Yes, sir.
Yes, sir.
Done? Yeah.
Sir, you said that we do the multiple groups on the benzene ring, the effect of that.
We'll do that, not today, we'll do that.
Okay, sir.
We'll take up that reaction in the last. Okay, we'll finish first and then we'll take up that. Done this one?
Yes, sir.
Okay. The last one here for today is Gutterman aldehyde reaction. Okay, so in this reaction, we are using benzene, and this is allowed to react with the first step, it is with HCN, then AlCl3 with H plus acid. In the second step, we are using H plus H2. Product is again benzaldehyde, CHO. So first step of the reaction, HCN with H plus, it converts into H C triple bond NH positive charge, because the lone pair on this nitrogen, it takes this H plus. Now, if you draw the resonating structure, we get this. This is the electrophile. which reacts with the benzene ring, HC double bond NH, positive charge on the carbon atom, and we get here this one, CH double bond NH plus H plus. This is what we have. This CH double bond NH is imine. Okay. Last step is nothing but the acidic hydrolysis, and this imine, you can understand this. It reacts with water, and we can write down the product like this: HOH, HOH. This 2 bond breaks. Less electronegative atom goes with more electronegative atom goes with less. So we get here the ring with CH, and 2 OH will attach over here, plus NH3. This goes under dehydration because 2 hydroxy group on the same carbon is not stable. The product is this. Okay. These two reactions, Gattermann aldehyde, Gattermann Koch reactions, are important name reaction. So one thing is left into this one, that when the benzene has multiple substitutions, okay, more than one group, like OH we have discussed, there's only one group present. When we have more than one group present on the ring, right, 2 or more groups present, then how do we get the product into this one? Not much in this one. We'll take up this next class. Okay. So we'll finish this and then we'll move on to aldehyde ketone chapter. Okay.
Yes, sir.
Yes, sir.
Fine. So this is it. Like I said, you can attempt questions of aldehyde and ketone. 60 to 70% questions you can do. Only a little bit of preparation reaction you cannot do. And whenever you see Cannizzaro reaction, aldol condensation reactions, Perkin reactions, those questions you can leave. Other questions you can try easily. Okay.
Okay, sir.
Fine. Okay. Thank you. We'll see you in the next class. Take care. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.